Hi everyone, I'm Elliot Cordo. I'm Chief Architect at Caserta Concepts, and today we are going to talk about a project we did mastering customer data using Apache Spark. So let's jump into it. So one marketing slide. So about Caserta Concepts, we are a technology company. Data is all we do. We do everything from traditional data warehousing to more modern, kind of data engineering problems, data science, data in the cloud. We're an AWS partner and such. And we focus on quite a few industries, ranging from e-commerce to higher ed, ad tech, just basically anybody who has interesting data problems or the types of people that we want to work with. We were established in 2001. We do everything from strategy to implementation and, definitely education and writing and such. And coincidentally, we're going to talk about kind of mastering data. Our founder, Joe Caserta, published this book with Ralph Kimball about how to prepare data for analysis, and obviously preparing customer data was a big part of that, and a lot of this holds up even in a more modern data engineering paradigm. So just a little bit about the setup. The customer data integration was in service of a solution, so we'll talk a little bit about that, and then a little bit about customer data integration and how Spark fit in. So what motivated our solution was, basically this problem of how many people you can possibly know. So, I'm a nerd and I have a young family and I'm tired, so I feel that I don't know that many people anymore. Very socially minded people might say that they know hundreds of people. If you think about social media, people know thousands of people. If you are a social media icon, maybe millions of people. But in the end, it's been scientifically proven that humans can only know about 150 people. The number, I think, is actually 148. And it was proven by this professor, Dunbar. It's called Dunbars Number. And he figured this out by studying primate behavior as well as human behavior, and kind of empirically derived that you can only have stable relationships with about 150 people. So maybe 150 is enough, unless you're thinking about business. So I think it's said that everybody in life is a salesman, right? So if you can increase this number, obviously, like kind of CRM 101 concepts, more people the more you can exploit those relationships. Exploit's maybe a negative word, but you can use those relationships, leverage those relationships for opportunities to find new business, to help close in business that's out there with those opportunities, higher closing, and then obviously successful outcomes and higher closing, you're going to get more revenue, which is all really good stuff. Again, kind of CRM 101 concept. But as you can see in the background, CRM kind of has this idea of aggregating all this data about customers, but what we were more interested in was kind of the linkage. So a very successful project that we did internally, which started as a summer internship project with some engineers internally and some interns to keep them busy, was building this social graph for us, based on internal and external data. So this involved our, kind of internal systems that we use, as a boutique consulting firm, our Salesforce, our email marketing systems, our corporate email, along with some social channels which are really important to us, such as Meetup, Twitter, and LinkedIn. And so we ended up building a social graph, platformed on Neo4j. We were able to run pathing algorithms like, how do we know somebody at company XYZ, or do we know CFOs in the financial industry in New York City? How are we connected to these people? And it's been really useful for us. And we developed it in Python and Neo4j because we like those technologies, and it was a productive, easy way for us to do it. And then, because we were so proud of our thing, we talked about it casually with customers, and they want us to build it for them. But unfortunately, it wasn't as small as our little boutique consulting firm data set. They had a much larger data set, 6 million customers. It's pretty dirty, 30% duplication rate. The event and linkage data, pretty large, not big data, but hundreds of millions of customer interactions that we had to aggregate and rationalize, and lots of channels, like more than a dozen channels, and few direct links across these channels. So, really no, accurate join keys that we could use to, pull things together very easily. So we decided, we did some tests with our Python code and realized, we're kind of lazy, it's not performing very well. Let's try Spark, which is something that we use a lot in our discipline. Spark has become kind of our de facto engine, so we gave Spark a try, just out of laziness and interest, and it actually worked out pretty well for us. So we'll talk more about that, but just in case you guys aren't familiar with these concepts, so a really important thing is that throwing a bunch of unrelated points in a graph is not going to give you guys a usable solution. This is kind of a non-truth about like Hadoop, or at least a misconception about Hadoop and NoSQL, especially graph technology, which basically is the most flexible thing out there, that you can just put data in and you can get analytics out. You still have to apply some traditional data management techniques. You have to clean and normalize the incoming interaction and relationship data. Those are going to form your edges in the graph. And you also need to clean and normalize and match the entities, so the nouns in your graph, so your vertexes. The vertexes, one of the very important ones is the customer. So we need to master our customer, our contact data. So a little bit of background. So mastering customer data, some would say it's MDM, but that's kind of more conceptual. But what we're doing is customer data integration. So it's applying technology and rules and doing something to help integrate customer data. So CDI is defined as a process of consolidating and managing customer information from all available sources. So in more simple terms, we need to be able to link people together across systems. So if it is someone in a corporate email, or it's somebody through some social channel, or somebody in your CRM, you want to figure out who those people are so that you can build your solution properly. And it applies to things outside of our solution. So just a quick overview of the steps required for those not familiar with this process. So you get data that comes in and it looks like a mess. So you got squares and circles of different colors. Nothing really looks the same. It's very difficult to compare things. So what do? You go and you validate the data. So you pull out the data, which is going to cause problems with your matching, which is going to happen later on, or is going to skew the results or the analytic capabilities of the solution you're building. So you want to take out that bad data. So once you take out the bad data, you go through this effort of making everything look the same, so that you can compare apples to apples. So these circles and squares become these rectangles that are neatly shaped. And the goal there is to get, especially if you imagine something like an address data is dirty and looks ugly. So you're going to standardize it so that you can actually use it as a join key in subsequent processes. And then once that's done and you've got data which is all kind of compatible and linkable, you can go and match. And you can take your customers, match them across source systems, match them in terms of duplication rate internal to sources, and you essentially can group them together into clusters. And then last but not least, you're going to choose your survivors. So who's that single view of the customer that we're going to put in as our nodes in the graph, as our vertexes in the graph. And that's survivorship. We're going to pick people, and then we're going to give them the best attribution possible represented in our analytic solution. Again, in this case, a graph. So traditional, it still holds up, and we'll talk about how this translated to the solution in Spark. You're going to go and clean and parse names. You're going to resolve nicknames, diminutive names. You're going to root them. You're going to use deterministic hashes, phonetic representations, or even probabilistic matching on these names. You're going to standardize your address, split them up so they can be joinable, and you're going to clean up your emails and phone numbers, where you might have many of these things, many addresses, many emails, many phone numbers. So you clean them up, and then once that's done, you can join based on combination of cleansed and standardized data to create your match results. And that's all great. So you might join on name and phone. For those of you who have done this, it's pretty boilerplate, pretty simple. So that's all fine, well, and good, but there's also new data, which could be a subject in and of itself in terms of, kind of online data, and your web properties or even social data. And we kind of broke it out like this. So the top one is all about like kind of this late reveal. So, you have customers who kind of are anonymous for long periods of times, and then somehow they link to like a known profile. So like a good example of this would be, people are customers, but they use your public website and they've been cookied, but they don't log in for like a year, So kind of this late reveal situation, and that can happen in social media as well. Like they might have some handle and a name in some social media channel, and then all of a sudden they, put their Twitter handle or whatever, something that allows you to link it to something that you can understand, or their email address or whatever. So the reveal is something that happens a lot. A more complex case is this idea of like using like actual behavioral or statistical methods to link people together. Again, this is a whole subject of itself, but worth mentioning as we talk about this, where you might have to look at people's behavior in combination with the data that you do have on them to match them. So, an example of that might be people publishing the same content to multiple channels, in social media, or you've got a user who uses a mobile app and they're logged in and they use your website and they're not, and they do the same thing and maybe save the same favorites and so on and so forth, which can be used depending on how tight your matches have to be. But no matter what happens, and this kind of gets into one of the requirements of the solution, is that once you figure this out, either through more complex methods or just a late reveal of the customer, you got to go and recluster all their prior activities. So you basically have to rebuild a good portion of your graph and definitely kind of recompute your match results. So why do we choose Spark? To some extent, we just wanted to get weird and use Spark for this solution because we knew it could do it. But it was also kind of a rationalization of big box MDM tools, versus the ROIs that are really, really expensive, limited by licensing, typically limited by the scalability of a single server. A lot of these tools are very, very legacy, And the customer in question actually had not one but two of these big box MDM tools and data matching tools in the upper right-hand corner of Forrester. So we had those at our disposal, but we still decided to use Spark. So the reason we love Spark, just in general, is development is easy. Local and distributed development's pretty much the same. Has great APIs, meaning it's going to be really, really productive for the type of work that we need to do to clean up this data and match it. Little plug for Databricks. We use this for all of our kind of prototyping. It's super productive, super easy to get started with Databricks. And it exists, so it exists and is attached to Spark. That's another reason we like Spark. We're Python guys, so we were really happy that you could use the full universe of Python modules, which we'll talk a little bit about in a minute in the context of Spark. It's open source and free for deployment if you choose to do that. And it's blazing fast. And as I said, Spark has kind of become our go-to, Swiss Army knife for just about everything that we're doing these days. So something that makes us really happy is like, map operations, so being able to map functions against data and parallelize that. So a lot of the data cleansing and standardization that needs to happen in like a customer pipeline is passive. So you're gonna take data and you're gonna clean it up. You're gonna run functions against the data. And we use this for both the interaction data, like the larger data set of all the things that they did and how they interacted with us, as well as the customer data itself and the cleansing, the standardization. And what we can do is we have this huge universe of Python modules, a lot of them really helpful for doing MDM or customer matching sort of operations. So, address parsing, you've got US address, postal address, and there's a whole bunch. Everybody has their favorites. You've got the fuzzy library if you're doing stuff with names, phonetic hashing or things that are more advanced. And just because I like the name of the module, there's sex machine. which can be used for generalization, which is the coolest module name ever. And it actually works really well too. So it's not just that it's a cool name for a module. And then of course all the goodies of standard library and everything that exists on Python or academia. So now we can parallelize these works across a large number of machines. So a little snippet of kind of sort of pseudocode extracted from the pipeline. So we import US address, which is a module, and then we essentially map the tag method against this existing data frame to split the address into its components, city, state, so on and so forth. And that applies for all the operations that we need to do in the pipeline that are more passive in nature. And then in terms of the matching process, once we've run a bunch of these map operations and also filter operations to clean up the data, we then have standardized linkable data. So we need to resolve the links between our customers. So how do we do this? We resolve it using self-joins on the large customer table, which in the grand scheme of things of data is not that large. It's 6 million customers. Even if you have 60 million, it's not that big of a deal. So in this case, we can use SQL, and here's an actual SQL statement where we're doing the self-join and trying to find matches based on a hashed name representation, which includes some fuzziness, and phone number standard. But we could also be including custom Python functions in the SQL or just about any operation that we want. So after this is done, we get match output, and it's not very useful. So it's basically a table of this guy matches this guy and why, right? So, it's a good output. It's definitely a part of the journey in creating clusters, creating survivors and everything. But, it's not very easy to kind of use this data. So where's our survivor? Like who's a survivor, and how do we link all of these duplicates or these cross-references to that ultimate survivor? So it's not really clear that 1, 2, 3, 4 matches 1, 2, 3, 5. And there's a lot of noise in the data. There's joins going both ways. The first row and the second row are, the same join, just same criteria, just matched in the different direction, which is fine. And we need to cluster this, so we need an output which is like a good cross-reference of duplicates to survivor, as well as a distinct list of survivors, because that's going to be our vertexes in our graph that we're building. So a little trick that we learned out of kind of laziness in original Python was abusing the networkx library for this purpose. So instead of thinking this about a table, because your mind immediately starts thinking, okay, we got to iterate and kind of unroll this kind of mess of matches, we thought about it as a graph problem. And if there's one takeaway from this, if you're not going to do MDM on Spark, which is totally fine, kind of trying to identify graph problems and using them to easily solve things is a good idea. So instead of seeing a table that was really ugly, we saw it as a graph that looks like this. And then if you think about it in the grand scheme of things, this is kind of like a bunch of communities within a larger graph. And that's great because just about every graph library has a way of working with communities to get the output that we wanted. So all we really needed to do here was to import this results, this XY, into a graph and then dump out our communities. So GraphX has this great algorithm called connected components. And basically what it does is it takes every node in a community and it labels them with the ID of the lowest numbered vertex. So basically, we use this lowest numbered vertex as our survivor or our cluster ID. So this isn't like our field level survivorship where we're building our best record, but we're just choosing somebody and we're using it as a pin to create that cross-reference that we can use to import data into the graph. So unfortunately, being Python guys, there was no Python API for GraphX. However, Scala seems to be, pretty easy. You just put var in front of everything and it seems to, val in front of everything and it seems to work. So Kevin muddled through that, and now he is going to explore more Scala. So yeah, basically we build a graph based on an RDD of nodes and RDD of edges, which is literally that table that I showed you before. You run connected components and you dump out the vertices, and you have your survivors list in your cross-reference. So another kind of trivial thing is once that's done, we do our field level survivorship. We basically use some windowed functions through kind of the functional paradigm of using Spark, and we choose attributes based on either the latest reported or the most frequent. You could write more complicated logic if you want, but we create survivors. So the thing that you guys probably wanted to know is with this data set, which is kind of largest, with approximately 6 million customers, hundreds of millions of data points, and we had the liberty of comparing it to 2 big box enterprise MDM solutions for doing a similar data pipeline. Was Spark faster? And I'll also add the caveat, was it more productive, or as productive as dealing with these tools? And I'll answer the latter before I go to the next slide, which is the big reveal that, yeah, we found it to be, roughly, just as productive as, taking boxes and dragging lines and, behind the scenes writing some code to do the things that we want in the big box tools. We found it to be very productive, and we were able to accomplish what we needed thanks to all those Python libraries very effectively. So the answer was Spark was actually a lot faster, than the big box tools. And I was kind to the big box tools because they were actually slower than I represent them, but I didn't take accurate timings. So on the map operations, where we're kind of cleaning, standardizing, performing these passive transformations on the data, basically a 10x improvement on somewhat similar hardware, but scaled up to 4 nodes instead of a single server. And this is completely linear. So if the data set got much bigger, we could add more nodes, and we would get the job done in the same time. And we did some tests to kind of prove that out by increasing this cluster size and reducing the cluster size. It was completely linear. But the real winner was kind of this graph trick as well as the survivorship. So anybody who's done this and this MDM operation before, it's kind of ugly. That's the thing that takes forever. So again, kindly, I didn't measure this part that accurately. It took more than 2 hours. In Spark, using Spark SQL to create our match results, and then using GraphX to kind of create our survivors that we can import into the graph. It took under 5 minutes. So each match criteria within the pipeline took maybe 20 seconds, and our connected component itself, when we create the clusters, took less than a minute. I think it takes 45 seconds or something like that. So it was surprising. We were lazy and we wrote less code and kind of used GraphX maybe in an interesting way, but it was super fast. And just for the benchmark, we were loading the RDs from S3, creating the matches, running building the graph, running connected components, and storing the results back S3. So that's kind of our benchmark. And then just also as a note, Neo4j did remain the persistence layer. We only used GraphX kind of for data processing. In the end, people wanted to run analytic queries and interact with this data, so the data still went into Neo4j in the end. I noticed I didn't include that in the presentation. So so Spark was a big win, and we're glad we tried it out, and was very successful. So just one small plug. So we run the BDW meetup, which has 3,000 members, and we meet once a month and talk about interesting stuff. You should definitely come check it out. And we promise not to mine your meetup social information for anything bad. So definitely come check us out if you can. And with that, we could take some questions if you have any. Yes. Yeah. Yeah. So I think I got the full question. So what's kind of the what was that? Mic?
There's a mic.
Oh, I guess I can run it over.
We're going to run it over. You want me to run it over, Dan?
Yeah, if you can.
Next question.
Okay, next question we'll get you. Re-engineering costs. So I think it's probably two parts. So if you have an existing solution that works and the concept is that you're going to totally re-engineer it on the platform, yeah, it's kind of large because it's apples to oranges. It's a complete rewrite or re-platform. I think in terms of like the skill sets, obviously the skill sets are a lot different. I think one of the promises of these MDM tools is that you can have less technical users and developers with more of the business concept in mind, developing the workflows versus somebody who's more in the code. So, I think that's probably the biggest change is like the cultural shift and the skill set shift that, moving away from the MDM tools or using only parts of the MDM tools. And obviously, customer matching is like only a subset of what a lot of these tools do. They also have like data stewardship flows and the things that really support a more broad MDM process. So that, you might still use your tool for even if you did decide to take this approach.
I think so.
Thanks for the, okay, there we go. Thanks for the talk. You mentioned that you were using GraphX for a computation layer and Neo4j for a persistence layer. So can you talk about the interoperability of those two, or did you actually use them together, or were they just parallel for different use cases?
They were kind of stages in the pipeline, so the Neo4j ended up being the target. So this is the thing that people are going to interact with, Cypher queries, UX, how they're going to actually interact with the data. GraphX, in our example, was kind of used as a ETL trick. So we used it to just do our clustering in Survivorship, which is kind of one of those standard steps in customer data integration. So the interoperability between the two, we didn't exploit any of that or do any of that. There was basically a handoff where GraphX landed some results, or Spark landed some results, and then that data was bulk loaded into Neo4j.
So, out of the 6 million that you started with, what kind of proportion did you end up getting an actual matching on, and did you do any comparisons between the box tools and what you got to see if the results were the same or similar?
Yeah. So it's a good question. So the 6 million, there was, so the 30% duplication rate is a little misleading because what we really had is like cross-channel duplication. So like it wasn't that there was broadly across all the channels a 30% duplication rate, but we'd say like within their main CRM systems they were quite duplicated. So we ended up with probably a little over 4 million, I think. Do you remember the number that?
Yeah, it was 4 million.
4 million something final discrete gold records. It was on par from what we were getting out of MDM. Some overmatching, obviously some undermatching, really different techniques. So the MDM, which was being used for kind of their data warehousing solution, obviously had been around a long time, so it had all those edge cases handled. This was relatively, we hadn't built for all that yet. But it was fine for what they were trying to do with it. It wasn't, critical decision support. It was more opportunity mining.
Can you provide some more information on what's the input data size? Like you said, hundreds of millions, maybe 100 million data points, but how many in GBs or terabytes? And also, if you have any input format have you used Parquet or any, the data is coming from any database directly as tab delimited? That would be great.
Hello? Oh, sorry. So that's a good question. That's a good question. So the input data size, a couple terabytes. As I said, it wasn't huge data. And when we're talking about input size, we're also talking about the interaction data, not just the distinct list of customers and their attributes. Once projected, it became much smaller. I don't know what the intermediate data sizes were, but less than a terabyte. The input format was varied. So we had to actually do ETL in Spark. So some of the data was through API, so it was JSON. The customer data and some of the stuff that we got from like their ERP systems and CRM would be tab delimited mostly. So it was a mix. Intermediate data format, I think Parquet. Yeah, I think Parquet by default, yeah, was the intermediate data format. Okay, cool. Thanks.